So as I was mentioning, I am not going to give the proof of the isomorphism theorem. Okay, it's technically I was initially hoping to give it, but it is too technically daunting. Although I made some bold statements about getting technical, nevertheless I have now chickened out of it. Okay, but I want to point out the following thing, that Amri is proving a sort of a poor man's version of the isomorphism theorem. I mean a baby version. So let me note note that the following is being proven. Note that the following is being proved by Amri in his lectures. If it is not proved, then it is almost there. Okay, you can then it's at the level of homework to finish the proof. And that is the following: if we have, so what does our isomorphism theorem say? That if I have two paths pi and pi prime lying entirely in the dominant Weyl chamber and ending at the same point, then the crystals what is that color directed graph that we constructed B pi is isomorphic to B pi prime. That is the statement, right? So this crystal graph and the colors Amri was drawing is precisely the same graph. That crystal is B pi is a crystal. Okay, so he is going to prove the following theorem, which is a particular version of the isomorphism theorem. Okay, so I am quite happy that some version is being proved. Okay, so so what is the version? So if W in A and W and W prime in A and star are of the same weight and Yamanouchi, then the crystals they spawn or they generate are isomorphic. So this is a version of the CDG isomorphism theorem. So let's understand why. Can any of you please explain this? Do you see why this is? Why is this a special case of the colored graph isomorphism theorem? So we specialize to the case of G is equal to SLN, okay, or G is equal to GLN actually, okay. So instead of a general, Kac-Moody general symmetrizable Kac-Moody Lie algebra, I just specialize to this case, okay, and you are considering special kinds of paths, right? So you may interpret every element of, so interpret J in A and star as the path, as the straight line path to epsilon G from the origin to epsilon G. Okay, this n is the same as this n. Sorry?
J belongs to A. You are in the later, right?
Yeah. Okay, fine. Correct. Right. So each letter is a straight line path, and you form words, right? So concatenation of words. Any word is just a concatenation of these letters, and therefore it's a concatenation of paths. So we can interpret A and star elements of A and star as paths. Just to be very specific about this, so if I'm as Amri was writing, he was writing W1 or A1, right? A D, right? Path of length or L was, what was he writing? L, right? So if I choose, if I take this, it is a path of length L in A and star, meaning each of these, this is between 1 and n, this is between 1 and n, right? How do you interpret this as a path? This is associated with the path that in the reverse direction, that goes to A. So with the path, if you wish, so I go in L different directions and we end up at this, right? So if you want to be really precise, so let's be precise and write it. So I start at 0, right? And I travel to epsilon L. Okay, and how much time do I take? 1 by L. Okay, from there I travel to epsilon L plus epsilon L minus 1. How much time do I take? 1 by L, right? And so on. Is this clear? So this finally, I'm here a 1 by L meaning by the time I get here I will have taken 2 by L. Thank you. This is epsilon A sub L. Thank you. This is epsilon. Too many subscripts, but right? So this is what? What is this point? Epsilon AL plus epsilon AL minus 1 plus epsilon A2. And what is this? Epsilon AL plus epsilon AL plus n minus 1 plus dot 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 plus epsilon A1. Okay? I do this. And what does it, so if I do this, then to say something is Yamanouchi, this is why he was doing it from the right, because we are interpreting it from the right. Now what does it mean to say this is Yamanouchi? For example, I take 2, 1, 1, that is Yamanouchi, right? So in the pictures that we have been drawing, in the dominant Weil chamber, because see, with n equal to 3, this is our picture, right? Epsilon 1, epsilon 2, epsilon 3, and this is the dominant Weil chamber. Okay, and so for example, 2, 1, 1 is Yamanouchi, meaning if I go, so this is interpreted as first going to epsilon 1, then going to epsilon 1, and then going to epsilon 2. that lives entirely in the dominant Weil chamber. So let us take some other, if I take this, that would be going here first and then going here. This is not dominant, but this is not Yamanouchi either. So you can easily see that being Yamanouchi is precisely saying that the paths lie in the dominant Weil chamber. So Yamanouchi, a word is Yamanouchi. So what is this? Okay, let's call this association. So let's call this AN star, an element of W. Let me call paths pi W. Is that okay? It's the corresponding path. Okay. So this is a one-to-one correspondence between such paths, not all paths, and words. So words are special kinds of paths. Of course, in my general isomorphism theorems, I can take any path, piecewise linear. So for example, I can take the straight line path, right? So Amri's course does not deal with that straight line path at all. Okay, it is proving something for these special kinds of path where you go along the, it's a concatenation of straight line paths. But that's something because we have not proved the general theorem. So this is a substitute. That's why I called it the poor man's version of the isomorphism theorem. Okay, so here is the observe. W is Yamanouchi. If and only if pi W lives in the dominant Weil chamber. So are we done now? Then the crystals they generate are isomorphic, meaning, so you start with this word, Yamanouchi word, and then apply this EI and FI, okay, and I get various, he was generating the crystals, right, and he gave the formula for writing FI, how to compute this I to the power R, J to the power S, etc. I hope you realized that he was just redoing the definitions of the EI and FI that he had done. Nothing more, nothing less than the same EIs and FIs. Okay? Because when I draw, if I have a path like this, so he was freezing things, right? So what does freezing things mean? So let us, this is a very quick, let me explain how you think about it, right? As a path, a word as a path. So to apply Fi, what did he do? So let's use the same notation that was being used in the morning. I is fixed. I plus 1 let us call J because I plus 1 is too long. Okay, J. So I have I and J. I want to apply Fi. What do? I freeze everything that is not either I or J. Why is this done? Because if it is not epsilon 1 or epsilon j, yes. See, the root I am applying is epsilon I minus epsilon j. Okay? If it's not going to act on anything else, right? It's not going to act on any other epsilon case. Okay? So if I start drawing the graph of H pi W I, right? So W is my word, this is my path, and I start I is my corresponding to the simple root I. If I start drawing this path, how will it look? Whenever there is, it's not I or J, it's constant, stays there, it's flat, it's like this, right? And when it is a J, when it is, how did you do it? First, Ji, right? Okay, Ji from the left. Okay, so one more thing to observe is I is going up, J is coming down. Okay, Ji from the left means J. If I have Ji here, but I am looking at it reading from the right. Okay, so which means it is like this, one step up and one step down. So the graph will go like this. If this is k not equal to ij, this will be j and this will be I. Sorry, did I? Because I am reading from this side. Which one? I will look like this, J will look like this. No, sorry. Right, correct. So, yeah. So, a portion corresponding to I is going up. A portion corresponding to J will come down. Okay. So, I am reading it like this. Okay. So the portion corresponding to I is going up, the portion corresponding to J is coming down. Is this what you are also saying? Correct. Okay. We both agree. Okay. This is how the picture will look. Now, if you start applying Fi's or EI's, you see these won't make any difference, and anything like this it will not affect, nothing will happen to it. Okay. So, what will finally it is I to the what notation did you have? I to the R, J to the S, but we are reading from this side. We are reading from this side, remember? So, it will look like J, so all these are cancelled out, something maybe, okay, so let's try to draw this. So, there are some cancelled portions maybe, right, and then come down J to the R, this is R, and I to the S. So, this is S. Okay. Now, so if, what was the condition? If S is bigger than R, then you apply, you can apply an F, right? I'm getting everything mixed up. So, what was his notation? I to the J to the, so which one came first? I, okay. I power R, J power S, okay. This is J power S, I power R, okay. I am reading, remember, from this side. So, I power, is this J power, right? Okay. So, when I apply Fi, let's just apply Fi and, so to apply Fi, what must I do? There must be some, so the minimum, right, the minimum, and then one more, okay. So, if R is bigger than 0, right. So, if R is bigger than 0, then I can apply, and then what happens? One of these, you cut this off here, reflect it, and then it comes down here, right? Correct? Okay. That's precisely doing one more J and one less R. It is Y to the R minus 1, J to the S plus 1. Correct? Is this okay? I'm not doing too many things very neatly, but he has already given you the definition. You know the definition of the E's and IFs. All you need to do is go home, sit down, check for yourself that the definitions match. Okay? Okay. So, and similarly E, what is E? Oh, did I do F rather than E? E is from this side, right? E is I shift this up. Okay, so you make J one less and R one more. That's precisely what was going on. So you observed this. So the yes. No, I don't need to. But since we were just doing everything between 0 and 1, I was just being a little, for once I was being a little careful. Huh? You can, but the way we have defined a path was always from 0 to 1. Yeah, but those paths, when you say yeah, I can just, you are right, I can just take the concatenation of pi, correct. By definition, if I concatenate, that still goes from 0 to 1, correct, absolutely, correct. I don't need to have been, but by the way, this is not a, I mean, the only reason why I took the times was just to make sure it was between 0 and 1, that's all. Okay. Concatenation also does the same. So I don't need to be okay, correct. But see, up to reparameterization, we are not worrying. So, right? Okay. So, good. Okay. So, is this clear that what he was doing, I was trying to judge, but it didn't seem like, so please do make the connection. So, what he is doing is what was done last week by Vishwanath, right? It's the same definitions in this very special case, okay? So, and so the sigma I was nothing but the while group action I defined. Si is just S alpha tilde that I defined, okay? It's exactly the same, right? So that means the graph, the crystal he was talking about, are precisely the colored directed graph that I defined, okay? And he is going to prove that they are isomorphic. So we have, in a very special case, the crystal graph isomorphism, the colored directed graph isomorphism. Is this clear? Okay, good. Okay, any questions on this before? I want to make one more comment about what he was doing this morning. And I will make that, but first, is this okay? Any questions?
So other classical cases and various words, AM type A is to naturally coincide with the words. What happens to type B?
Type B. So if you okay, what is the question? Of course, we have the colored directed isomorphism. No, now we have the proof. Okay, now you can define words. Maybe Digjoy knows more about this. So you can definitely you can define tableau. Okay, maybe I will come to that slightly later in today's lecture, and we'll. There is another. This is one interpretation of word. One interpretation of paths in GLN. There is another interpretation, okay, which I will maybe come to slightly later in the talk. Depends on how it goes. But maybe we can just postpone that question until then. Okay. So any questions on this? Okay. So let us see. So this morning, so Amri was saying the Robinson correspondence, and he was drawing these maps, right? Okay. So I just want to point out one more thing that was implied in his lecture. Maybe if it was not made explicit, I want to make this explicit. Okay. Remember that he wrote this before doing this Robinson correspondence, etc. He gave this statement of Schur-Weyl duality, right? So let us take Cn star d, I mean tensor power d, right? And so this, you can think of this as a GLN module. So let me write the group and the symmetry group module, right? And it has a decomposition as a GLN cross SD module, okay, for every partition of D, right? You have this V lambda, which is a representation of GLN tensor. What was the notation he used? SP lambda. So as you may know from finite group theory representations, every representation of this, complex irreducible representation of this, is the complex irreducible representations of this are indexed by partitions of D, right? And so this is the so you are there are as many partitions of D as there are representations of the symmetry group SD, but there are also exactly as many irreducible representations of degree D of GLN, meaning with D boxes. Okay, with D boxes. Of course, you have to be sure, see, this has to be correctly interpreted with the lambda is, there is an n, right? These partitions, if they start having more than n parts, then it doesn't make sense. So you just ignore those, just put them to equal to 0. Okay, so there is some here this will not make sense unless the number of parts is less than or equal to n. Okay, but modulo that. Okay. SP will be there. SP will be there. Okay, because that is for SD, and I am fixing a partition of D. So all the SPDs will always be there. Okay, it's only the V lambda which may vanish if my D happens to have more parts than n parts. Then that V lambda term will just vanish. Okay, you can just take it to be 0. Okay. Yes, because see, if, for example, GL2, if you take any partition with more than 3 parts, there is no representation corresponding. It's 0, right? Okay. Okay. So now let us run this. Look at the path model for this. Okay. So if you recall, so let me remind you that if I had V lambda and tensor V mu, and then there was a B pi, okay, let me call this lambda 1, lambda 2 for a change, and this is B pi 1 and pi 2. Oh, maybe I had this notation, so let me change again. So this is so here what is pi is a path lying entirely in the dominant Weil chamber and having endpoint lambda. Pi prime is a pi prime lie entirely in the dominant Weil chamber. Pi 1 equals lambda, pi prime 1 equals lambda prime. This is the assumption, right? Okay. Then this forms a path, so this forms a path model for V lambda, this forms a path model for V lambda prime, in the sense that those paths, if I take there are as many of them as the dimension. Moreover, if I take their endpoints and look at the character, I get the character of V lambda, etc. Okay, there are all these nice properties. So I call that a path model. Okay. Then what we realized is that there was this, if I take concatenation here, that is the shadow, if you wish, in the path world of the tensor product in the representation world. Okay, so there is this representation happening and tensor product of representations happening in the representation theoretic world, and it casts a shadow in the path level, on the combinatorial level, and that is the concatenation. Okay, so this is a path model for the tensor product. Okay. Now let's get back here. So if I have tensors of the same thing, this is, we've done it for 2, but the same thing is true for n or d or any number of tensors, right? Okay. Yes, Chani. No, it's not an assumption. It is not an assumption. It has all the, what all do I want? Okay. See, we have not defined what it means for something to be a path model. Okay. But what I mean is, it is a set of paths which, if I compute its character, I get back the character of this. Okay. Let's keep that as a minimum requirement. Okay. I may want more from it, but that's at least a minimum requirement. Okay. That we have verified. No, that comes because the character of B pi concatenate B prime is just the product of the two characters, and each character is the character of V lambda that we have proved. That's the path character formula. So it is clear from the path character formula that the character of this is the character of this, and therefore it's a path model. Okay. So I admit that we are using the word path model in a very loose sense. We are not being mathematical about it. No? Okay. So what is a path model for Cn, for the defining representation? What are paths for Cn? Epsilon 1, epsilon, so these are the straight line paths. So Cn has basis vectors, the standard basis vectors. They form a set of weight vectors, right? They are a basis consisting of weight vectors. What is the weight of Ej? If I take the diagonal and act the jth diagonal will act as, with that coefficient, the others will act as 0, right? Okay. So it is clear that the weights, it has weights epsilon 1, epsilon 2, epsilon n. Okay. Now just let me write 1, 2, 3 n rather than keeping writing epsilon. So I can say an is path model for Cn, correct? Just let us 1 through n, okay? And what is An star or An star d? So what was this? Of length d. Is that clear what I mean? Words in 1 through n of length d, correct? Okay. What is that a path model for? Just putting one word next to each other is concatenation. So this is, by this procedure, it's a path model for Okay, and what are you doing here? So what is this in the path level? What you can do is you take this path model. So it's a color directed graph with the E's and F's acting on it. Okay? Yes. Yeah, it doesn't matter. If you don't like it, okay? Yes. No, I'm just interpreting 1 through n as 1 means the path from 0 to epsilon 1. J means the path from 0 to epsilon j. You could. All. No, all paths meaning. No. See, we are not considering all paths for the entire path. We are considering for that representation. For that representation, I am choosing one path for every weight vector. Because that representation is of that form. So if for example, the highest weight for Cn is just epsilon 1. And if you generate the crystal, you will just get epsilon 1, all these straight line paths. It's n dimensional. So you must have n paths. And what are the n paths? They are just epsilon paths, the straight line paths. For example, if I take this, if this is my highest weight vector, and if you act f alpha E alpha on this, you will only get these 3 paths in this case. Right. So that's what I mean. So this is path model. So correct. So this is if you want b pi epsilon 1. Okay. Correct. Okay. Path model for this. So that's what we are doing here, right? Okay. So okay. Now what is this on this side? What are we doing? We are taking this graph, right? This is a direct sum. This is, if you want, right? That's what is meant. Okay. So you are breaking this up into disjoint pieces. Okay. This graph. So this. We are coming down from the representation world to the combinatorial world. These representations get replaced by their models. The tensor products get replaced by concatenations. And you write equal to, and what does this direct sum get replaced by? Disjoint union. Okay? And since we are only looking at GLN, this is just like a multiplicity. So each one of these occurs as many times as the multiplicity of this. So what it means is, if I choose this an star d, this is what I get on this side. It is a disjoint union as lambda varies over as partitions of d, right, of b lambda, right, to the power dimension of sp lambda. Right, this is what you get. B lambda means path model for the weight lambda, because I have V lambda here. What is the path model for that? I can write B lambda. I mean, I can write B pi for where pi is a path in the dominant while chamber which ends in lambda. But then all of them are isomorphic, so I can write B lambda, right? Or you can write LS lambda. That's you can yeah, but right? Okay, is this okay? Okay. Now what the Robinson correspondence is giving is giving this. It's a nice interpretation of this.
Power is in disjoint union of B lambda.
Thank you. Thank you. Thank you. Thank you. Yes. What is that? Direct sum in the category of sets is disjoint union. Did I say that correctly? Direct sum in the category of sets is disjoint union. So I should write disjoint union. Okay, thanks. Yeah. Yeah. So now you see this P and Q business. If I take a word here, so this word, so here there is this, this is Robinson, gives you P, W and Q, W, right? Okay, so I will draw a picture. Okay, let's take this, the Q to be the Q axis, this to be the P axis, right? And so these, so if you wish, for every, so you have a disjoint union over lambda. So in fact, how to say this? Okay, so let me just say, if all those which have the same, all those words which have the same Q fall in the same B lambda. Okay? Right. So you can say for every lambda occurring here, right? I can see the number of times it appears, etc. I'm not saying this very well, I'm afraid. Okay, let me just say the following. In this picture, this is a disjoint union, right? Okay, so let's for simplicity say this is B. Did I use? Okay, so this is not right. This is lambda. So let me say, should we write this just for? So let's write dot dot dot. So I expand it and write it out. Okay. So in this picture, so what I'm saying is, so here this is a disjoint union. So all these, so you plot the P and the Q, right? P on this axis. So each of these will get mapped to a point. This is a bijection, correct? So every path here I can represent by a point here, because this is a bijection, correct? So there are points here. I plot, right? And all those which have the same value of Q, right? Q constant. Q constant are precisely the B pi ones, B lambda j's. So this is one B lambda j. Anytime you have the same Q, that is one. So verticals, let me call them verticals, are B lambda j. Okay. Moreover, the horizontals, so to speak, okay. So if two of them have the same P, in particular the shapes must be the same. the lambdas must be the same. So, for example, if lambda 1 equals lambda 2, but so let's say I have 2 points here which have the same P and different Q. It's the same P. So the Q here, so let's say this is Q1 and this is Q2. Okay, this is Q1 and this is Q2. Then the shapes of Q1 and Q2, Q and this all are the same. And what this means is that as I vary the P, I move in the same so you see with a given Q, I said that it's a B lambda J. So you just concentrate on this line now, this vertical. What is there is a colored directed graph. What is here is a colored directed graph, right? And this could be a very big colored directed graph, and P is a point on that colored directed graph, and if two things have the same P means those points are in the same relative position in the colored directed graph. So for example, if this was obtained from the top, meaning from the dominant path, unique dominant path in its crystal graph, by applying F2 twice, this one will be obtained from its unique dominant path in its crystal graph by applying F2 twice. Is this clear? Okay. So the horizontals indicate the same level in the color directed graphs. So that's a vague statement, but I hope you understand. Is this clear what I'm saying? Huh? So that's a very beautiful picture because you have this Schur-Weyl duality and there is this Robinson correspondence, and you have this colored graph, this tensor product model. It all fits up very nicely. It's an absolutely gorgeous picture if you ask me. Okay. Okay, so let us talk about okay, now let me just come back to the de Mazur character formula and finish the proof of that. So back to proof of the de Mazur character formula. Yes, Shamik. Yes, it is. That is true. But how do you? Yeah. Correct. So you are assuming that the Q could vary over standard Young tableau. Yeah, that's correct. That's correct. Yeah. Okay. So, okay. Now let me be. So we had almost come to the crux of the proof. We had arrived at the crux of the proof when we ran out of time yesterday. So let me just remind you of the notation and the point that we were at before telling you. I mean, we all we have to do is wave our hands a little bit, and the proof is done. Okay. Just so let's recall where we were, stare at it, wave our hands, and we'll be done. Okay. So where were we yesterday? So recall what we were proving, right? What is the statement of the de Mazur character formula? So it's the path version. So assuming so this is the path de Mazur character formula, assuming the de Mazur character formula itself, which said that if I take this de Mazur operator indexed by W, acting on E lambda where lambda is the dominant weight. So this is our notation, W is in W. Okay. Now this is equal to character of the de Mazur module, this. This was the statement. Okay, this we assume. Okay. What were we wanting to prove? So what is this? Recall the statement. So statement is that the character, okay, let me write it this same way. So if I take paths, in the de Mazur character formula, there is no model. There is no model. It's just, no, there is no model. Just like the Weil character formula, there was no model. So you wrote e to the power, sigma sine w, e to the w lambda plus rho. There was no model, right? You started with this weight lambda, added rho to it, then you said do this, do this, do this, and lo and behold, you get a formula. Right? This is similar. These operators, just operator, see this lambda w's, remember, are operators on, these are, right? It is just, they operate on weights, right? And it eats a weight and or even a linear combination of weights and spits out another linear combination of weights. That's what it does. Okay, there is no model. Okay, so that's the point. See, so if you remember the triangle picture that I wrote last time, so there are representations and there is this combinatorics, right? So here there is no model. It is from the representation picture directly to the weight picture, right? What we want is we want to insert a model, okay, and a model on which which is, for one thing, we don't want to keep too much information because, like I said, it involves cost, meaning representations are difficult to handle. We cannot do too many things. They are very big objects, right? Okay. On the other hand, just keeping the weights themselves or the character formula isn't also good enough. Okay, we want to keep something just a little more extra, and that is the model. Okay, for example, it could be tableau. Tableau are not just weights. Each tableau has a weight, but it is not just that weight information. It tells you where that 2 is, where that 3 is, right? That is a little bit of extra information that you keep. So the tableau give a model. Okay. Now so we have worked with tableau model. Ravinder also worked with the pattern models, right? There are so many models. Now the path model is sort of the ultimate model as of date. So because it subsumes all models. Okay. So here what we are doing is, the point is we want to lift this operator to the level of paths. So what I will do is, here is the representation picture, here is in my triangle that I wrote on this board, representation picture, there is the weight picture or the combinatorics picture. Now I have this, I want to insert something in between. Okay, on this model, on this world, in the path world, I want to lift this to the path world. So remember, the first thing we did was to lift the Weil group action to the path level. Now we want to lift the de Mazur to the path level. Okay. Okay. So let me write the statement. It says you take all, eta, let me call it, eta is in Ls of lambda with initial direction less than or equal to W lambda. This gives the character of V. Okay, take all those paths which go in, of whose the initial direction is less than or equal to W lambda, and that gives the answer. Okay, that's what we want to prove. Okay, so how are we going to do this? So we do this by induction on. So let me remind you where we were. So proof was induction on length of W, right? So W is equal to identity. The trivial case is easy because then this is just the one-dimensional module. The de Mazur module is just the one-dimensional module, and how many paths? This is just lambda itself. So how many paths can start in the direction of lambda? Only the straight line path, because after I go in the direction of lambda, I can't go in any other direction because the directions have to decrease, right? Lambda is the least direction. So once I start in the direction of lambda, I have no choice. I just keep going in the direction of lambda. Okay, so that is the proof that in the identity case we are done. Okay, because the endpoint will just be the straight line path lambda ending at lambda, so eta 1 will be just E lambda, and both sides evaluate to E lambda. Of this is E lambda, and this is also E lambda. Okay, so now let's assume that, right, W is equal to S alpha V with length of V less than length of W, and alpha is simple. You can always find such a alpha. Now, by induction, you know that this is true for V, right? So, by induction, what do you know? So, character of, so let me write it in the same direction. So, let's call this set. I don't want to keep writing this. Let's call this Ls lambda W. Okay. So I will write eta in Ls lambda V e to the eta 1 is equal to character of V lambda, right? I know the theorem for V, right? I want to prove it for W. Okay, so and here is but what do I know about by the de Mazur character formula, right? What do I know? Know that, so no, by DCF, not the path version, just the ordinary version, right? That if I apply to the character of V lambda, this is, I'll get what I want, right? Remember what this was. For this, you could choose any reduced expression for W, and to prove that, I just choose a reduced expression for V and then build my reduced expression for W by just taking that string, right? And so, this means I keep applying E lambda, and if I, keep applying this, what is that, lambda, the de Mazur operators. So if I apply up to this point, I would have got character this by the formula, and applying this. Okay, so so let's apply So if I can apply lambda alpha on both sides, I am done, right? Okay. Okay. So, and let us look at what this, okay. So apply, okay, and this side is what I want. Okay, I have to analyze this side. Okay, there are 2 points here. This was what I was trying to make yesterday, but maybe didn't do a good job. Hopefully, I'll make it today. So the observation about this is, so this is, so that is V lambda is a B module. B is the Borel corresponding to the G, right? So it's a B module that is the restriction, okay, in particular a B sub alpha module. By that I mean B of the SL2 alpha, okay, that is the restriction of a finite dimensional SL2 alpha module. Okay, why is this? So by induction, if you wish, this is a finite dimensional module. Okay, any finite dimensional submodule is contained in a finite dimensional SL2 alpha module. Okay, by the integrality property. Okay, and therefore this is a, you know, it is a B module by definition, and this I have explained. Okay, so what this means is the following, that if I write out the weights of this, okay, so this means, this implies the following, and this is an easy exercise, maybe I'll not maybe easy, I'll say this is an exercise which you should definitely do, right? If you are studying Lie algebra representation theory, then this is the kind of exercise you should sit down and understand completely by yourself. Okay, so what this implies is the following. So remember what, it's a finite dimensional SL2 alpha module. The weights will look like, they will be the alpha, if I apply alpha check, they will be evenly distributed around 0, right? Okay, but here it's only a B module, B alpha module. Okay, so what will the weights look like? So here is the claim. So this means the following. If let you list out the weights of this. Okay, let mu1, mu2, etc. be the weights of V, okay, listed out with multiplicity. Meaning if if the same weight occurs 5 times, I write it 5 times. Okay. Let n1, n2, etc. be, ni is mu I alpha check. Now I am fixing this alpha. Okay, so these are some integers. My n's look like eta. Okay, the claim is if mu I, if n, if for some j, nj not equal to 0, sorry, nj is less than 0, then let me say this correctly, mu j, which is the corresponding mu, right, minus or plus alpha mu j plus 2 alpha, etc., and mu j plus n j alpha. Just one second. Do I want n j alpha or n j plus 1 alpha? N j alpha. So this is absolute value of n j alpha, okay, or minus n j alpha if you wish. Then occur with multiplicity at least that of mu j. This is the claim. Okay. If something occurs, say with my minus 2, then that weight plus alpha, and if with multiplicity say 10, then mu, so mu is a weight such that mu alpha check is negative, let us say negative 2, and multiplicity is 10, then mu plus alpha occurs at least 10 times, mu plus 2 alpha occurs at least 10 times. This is the claim. Okay. From this, what you can deduce is the following, that suppose I start cancelling out so this is the upshot is, so the upshot of this is the following. I can divide my weight, so upshot is can divide the weights as follows, or can partition the weights. Right. So it's better to think of this in a picture. There I've written them horizontally. Now I'm going to write them vertically. I can make, so if I have a weight, say of, if this is my mu of weight minus 2, then this will also occur and this will also occur. Mu plus alpha, mu plus 2 alpha will also occur. So this is the alpha direction. Right? This is the direction of alpha. If this occurs twice, then these two will also occur as many times, and so on. Okay? So what I can do is, of course, this may have occurred because something else here occurs, but that means I mean, there is a little bit of back end, combinatorics maybe to just get yourself, get the hang of this. But what this means is they look like, so either the entire alpha string through mu is there, or there are some extra bits. The extra bits can only live above the axis. They will not lie strictly below. Yes? No, we cannot, no, not necessarily. Not necessarily, no. For example, you could have started with lambda, right? For example, I could take V to be identity. Then I just have one point which is lambda. Lambda alpha check is some non-negative number because it's the dominant weight. So it could be like that. No, no. See that that may not be possible. If the in the ambient module, yes. in the ambient module, yes, but not in the de Mazur module. Okay. So, but what we are worried about is the de Mazur module. Okay. I hope I don't want to draw the picture, yesterday's picture once again, but if you saw it, we had things like this, right? Maybe that's good, because so where was I? Let's see. This was my so this was my beta, right? I started something here, and this was alpha. So first I applied beta, then I applied alphas, right? And we went. It was something like this, and then if I want to apply beta to this, right? Maybe like this. I don't remember exactly. If I apply, so this is a string, and everything else lives above, so it's okay. So the picture always looks like, see, if I have something in the negative, it is always, you can put it in a string. It occurs in a full string. That's what it means. Well, I haven't proved this for you. I haven't proved this, but this is my claim. Okay, and this is an easy exercise. I mean, this easy meaning is an elementary exercise. Okay, which you could. Okay, so what this means is, and remember, yes, now what we did yesterday comes into play. How did lambda alpha act on this, right? So where were we? We knew that this was the picture for, this is my weights of V, sorry, with a V here, right? So what I do is, I just saturate, the lambda alpha, just what it does is, it fills this out. Okay, so these are kept as they are, nothing happens to them, meaning if I apply lambda alpha, of course individually it does something, but overall on the entire thing it just keeps it constant. Here it is kept constant, here it is kept constant. Remember, it's a linear operator, and here it gives me the entire, here it fills it out, here it fills it out. Okay, so, and here is, so so what I want to do now is point out that the path picture, so look at, so this is, remember what we were saying, we have the representation picture, we have the weight picture, and we have the path picture. Okay, so this is the weight picture. Okay, so for a minute, imagine that you could you could create a basis for this de Mazur module, such that these were highest weights for alpha. Just imagine, right? So that's, you could create, I repeat, you could find a basis for this, right, such that these were all highest weights for alpha. I mean, they have to exist such weights, by this fact, but we cannot get our hands on them, on such a basis. Then, of course, you would be done. See, at the level of weights, what is happening is, what is the de Mazur? What happens when I go to the next step in the de Mazur? That is, you will, lambda alpha. Then this gets filled in, that's all. Okay? Now, if, at the level of the representations, what am I doing? It is as if you are applying a y alpha also at that point. Okay? Let's accept this. It's when I move from V to W, It's like allowing yourself a y alpha at that point. Okay. Now, if I knew that there were highest weights with these weights, highest weights meaning on which alpha were 0, right? X alphas were 0, then the SL2 alpha module generated by this will be very good. Okay. So I know I have this weight picture. It is too difficult for me to get a representation theoretic picture which is like this, by which I mean when I write a dot like this in the representation picture, what I mean is getting my hands on a weight vector which when I apply X alpha is 0. Is that clear? That's what I want. If I had that, then I would be done, because then just applying a Y alpha to this picture would precisely give me this would get completed, this would get completed, this would get completed. Okay, that's very difficult. Okay, now what the path offers me is an in between thing. What we will see, and it's trivial to see in fact from the definition, or rather very easy to see, that if I draw the paths for this, they have a picture like this, and where if I apply E alpha to this path, I get 0. When I apply E alpha to this path, I get 0. When I apply E alpha to this path, I get 0. So what I am saying is, look at the picture of paths Ls lambda V. No, see, these are highest weights only locally for the alpha. What I mean is that, see, there are highest weights at every new step. There may be, for example, in our picture, when I applied, this is the highest weight. I apply beta, I get here, right? And then when I apply alpha, I keep going here. And this will be a highest weight at the next step for beta. Okay? So, meaning x beta applied on that is 0.
At this stage, these are highest weights for
This is highest weight for beta. In that other picture, yes. These are. See, this is just a weight. This is just the weight picture. So you have to. There is a bit of subtlety here. This is the weight picture. This does not mean that I have a vector of this weight such that when I apply X alpha to it, it is killed. No. It just means that when I look at the set of weights, I can partition them like this. That's all it means. That's all it means. Does not mean that you can find a weight vector of that weight on which if I apply X alpha it is 0. Okay? So, that's hard to find.
We take this V lambda. Okay, now look at this parabolic moment, this Borer plus SL2 alpha generated by this moment. Okay. Looks like
that will be.
there was a BW of that.
Yes, that's correct. That's correct. That's correct. That's correct. Yeah.
So the character matches, and at that level it is SL2 alpha in the image.
Yes. Yeah, at that level it is SL2 alpha. So that de Mazur module corresponding, since W, S alpha W is less than W, so the de Mazur module is SL2 alpha stable.
So every time the weights are fine, only the multiplicity may not match. That's the problem.
No, no.
If you compare with V lambda,
Hmm.
what is going wrong?
See, V lambda has many more weights. Is there lots?
V lambda, no, but if I look at that,
Hmm.
weights of VW of lambda
Hmm.
and then weights of V lambda,
Hmm.
these weights are occurring there. So the multiplicities cannot
Not multiplicities, even the weights need not be there.
No, no,
Hmm.
I'm only worried about the weights that appear here.
Okay. They may not match. At some point, they start getting matched. After a while, at some high level, they will get matched. That much you can say.
But the weights actually, in some sense, they, whatever weights are here. Okay, I'm more interested in understanding weights of the resume model.
So are we. But that's okay. Okay. So the point is that so look at this. So observe. Can partition the paths in LS V lambda with picture looking as above. So if I look at the paths, right, then there will be a similar picture, okay, and where this time if I act something, you know, this is E alpha and this is F alpha. So if I draw, so why is that? That's rather easy to see. So if I have a path which is going in a direction less than or equal, okay. So what is the initial direction here? Yes, it is less than or equal to V lambda. Okay, okay, and what are all the paths? Okay, then the following can happen. So if I, okay, let me say that. If I start applying F alpha to it, okay, it may still be contained within V lambda. Okay, and the point is this: if I have a path whose initial direction is less than or equal to V lambda, okay, and the first time after I apply F alpha, right, it has changed, I mean it still continues to be less, then the second time, third time, fourth time I apply, it's not going to change direction. It's going to continue to, so what the upshot is, either in the first step itself, it changes, right? It is not any more less than V lambda, or it will continue to be in V lambda. Okay, so if at the first step it doesn't change, the entire string continues to be here. That's the point. Okay, and how to say, if I have a path which is, what else do I need to say this? So you have to analyze what happens to initial directions as you apply E alpha and F alpha. So another thing to notice is, suppose I have a path which is less than or equal to W lambda, right, which is going in less than or equal to W. then either it is already less than or equal to V lambda, or by applying sufficiently many E alphas to it, I can make it go to, I can get a path which is less than or equal to V lambda. So, for example, when I complete these two strings, I get all paths which are, whose initial directions are less than or equal to W lambda. Okay. So, the point is, when I complete this picture, okay, so there is this bit of lemma on paths. Okay, this is a good homework exercise on paths. Okay, you have this elementary definition of paths, and using that you can work this exercise out. Okay, so what happens to the initial direction, etc. So, for example, here let me write one. So, if sigma is in LS W lambda, then and E alpha sigma is equal to 0, then so let me make one more. Then E alpha sigma is also in LS W lambda. So, when I apply E alpha, the direction can only decrease, it cannot go up. Okay, then E alpha. Moreover, or 0. Okay, is E union 0. Okay, moreover, if what is that, E alpha sigma equal to 0, then sigma actually belongs to LSV of lambda, which means when I take LSW of lambda, take a path there, if it's already less than or equal to V lambda, okay. If not, I keep applying E alpha to it as many times as I can apply. The last time I cannot apply, meaning, so if I apply one more E alpha and it gets killed, at that point it already belongs to, its initial direction is less than or equal to V. What that means is, when I complete these strings, when I take the entire F alpha strings on these, I get all paths that have directions less than or equal to W, because starting from any one of those paths, by either it is already in V lambda, or by applying enough E alphas, I can get myself to V lambda. So, which means it belongs in this string. That's what it means. So, this is an illustration of the situation where you have lifted, see, I repeat, this is, after all, this de Mazur operator is it's doing something very elementary. It's doing something very simple minded. Okay? And we are claiming that that gives the de Mazur character formula, right? So, trying to prove that at the level of representations, this is the kind of decomposition you have, is quite difficult. Okay, but doing it, having a picture like this at the level of a model seems to be easy, and that's what the paths achieve. Okay, so the upshot is now that if I apply so finally, even if you have not followed what I said for the last 15 minutes, the point is, again, I'll use the word upshot. The upshot is that if I take eta in LSVW, eta, this is eta in LSW lambda eta. So, acting on the level of paths. Okay? So you have lifted the De Moivre operator to the level of paths. And what is the definition there? It's just like we mimicked the while group action definition. We just map a path if on alpha check its endpoint is positive, then we just take the F alpha string and just take the addition of all those. If it is the E alpha string, then if it is negative, then we leave that out and take the negatives of up to in the correct way, just mimicking the definition of the De Moivre operator on the weights. Okay? Okay, so maybe we should stop there, and so QED, let me write. So this finishes the proof, because this you know by induction is character of, so when I apply now, I apply this is at the level of, this lives, remember, at Z pi. Okay, now I take the map to, this lives in Z pi, and I take the map from Z pi to Zp, sending pi to pi of 1. Then this goes to this, and here I have eta 1, but this I know is character of V lambda. This is by the De Moivre character formula, not the path one, but the ordinary one. And sorry, that's not correct. This is by induction, because I have assumed this is the induction step. Okay, and this is by the De Moivre character formula, that this is V character of V. Okay, so finally, so QED is here. So we have this is equal to, but on the other hand, by this, you can replace this by this. Okay, so these three, this is by path lemma, lemma on paths. I mean this observation. Okay, so this is a lemma on paths, and this is induction, and this is De Moivre character formula. These are the three ingredients. Okay, okay, I will stop here.